Okay, so hello everyone. Welcome back to the fourth day of the Common Envelope Conference. I hope that you've been enjoying it as much as I did. And today we're going to start with talking about Common Envelope evolution in stellar populations. Try to go to the next slide. As Noam said, we have 5 talks lined up. I think it's really cool to see this combination of theoretical talks and also observational talks. I think it's really nice to have that in one and the same session. And then the organizers also asked me to give a bit of a review to start with and to highlight some of the discussion points that we can maybe address later on. So let me start with that. And I think the first thing I want to mention here is that it's, for me, a really exciting time to be working with stellar populations. And that's really coming from like the progress that there is in observations. So like 10 years ago and longer ago, we had samples that just had a few stellar systems in them. And now we're seeing samples come along that have several dozens, sometimes several hundreds, sometimes even several thousands of stellar objects. And I think that's just amazing to see. So of course, more systems is always better, but it's also like a very nice time because we're finally moving away from small number statistics. And that's, a very special moment. We also understand the selection effects much better because these samples are coming often from large scales automated surveys, which is really helping to compare them with theoretical modeling. And it also means that these samples are now extending in what they're probing. So in the range of masses, the range of periods, and more different types of binaries. So I think that's very exciting. Now, on the side of modeling, this is almost a bit of a huge blessing and a little bit of a curse, because it means that we can study these sources in a lot more detail, and that some of the simplifications that we've been doing so far are no longer valid to take. And so with that, I'm thinking of ignoring triples and quadruples, for example, and I'm going to come back to that at the end, at the last final slides that I have. But for now, I kind of want to give an overview of the 2 methods that have been used mostly to learn about common envelope evolution from these stellar populations. And the first one is to take an observed system and to calculate the evolution backwards in time. And this really relies on this unique relation that we have for giants between the mass of the core and the size of the star. And the really nice thing of this relation is that it provides a link between the post-common envelope binary and the pre-common envelope binary. So how does it work? We observe a post-common envelope binary, you measure the mass of the white dwarf, and we then assume, okay, the mass of this white dwarf is probably very similar to the mass of the core that the giant had just before the common envelope. That mass of the core gives us the radius of the star, and of course, the radius of the star at the moment of Roche slope overflow gives us the radius of the Roche slope, and therefore the period of the system. So with this, we can relate the period after the common envelope to the period before the common envelope. Now, this has been studied by several different groups. For double white dwarfs, I just mention a few of them here. And I just show one plot here of the derived periods for double white dwarfs in this case. So this is the period that the system would have when we have a white dwarf and just a normal companion. So before that last common envelope phase. And you see that we have periods of the order of 100 days, while the observed double white dwarfs have periods of something like a day or a fraction of a day. So this is showing you that strong orbital shrinkage that we expect from common envelope evolution, but it's quantifying that effect. So I think that is nice from this method. It also gives some unexpected things. For example, the first phase of mass transfer, so when that first white dwarf is created, that we do not see that strong orbital shrinkage. So this has led people to propose alternative common envelope phases, but in recent years, also more attention has been gone to studying stable mass transfer, very non-conservative stable mass transfer here. So my first discussion point would be which systems avoid common envelope evolution, which do not. And how can we understand this border better, right? This is typically done with detailed stellar evolution codes that are pushed into the regime of common envelope evolution, but that has issues and complications. So is there things that we need to be careful of, or are there other ways that we can learn about this? Now, if we go back to this plot here, the pre and the post common envelope periods, then if you have those two quantities, you could also constrain the common envelope efficiency itself. Now, you have to then assume a certain common envelope framework. And of course, the typical one then is the alpha common envelope framework. But I just want to mention that this is not limited to just one framework, right? We can try alternative dependencies as well. But if you assume the alpha common envelope framework, then here again, for those same systems, you see the derived alpha lambda. Now, one thing that becomes clear here immediately is that there's quite a range of alpha lambda that comes out. And this is partly due to the degeneracy of the method, that relation for these giants depends on the mass of the donor star, but it also comes from observational uncertainties on the measured masses of those white dwarfs. Also, the small number statistics don't help. We want to average over all of these uncertainties, average over the full population, but the populations are small. So you already see two immediately things that we can possibly improve. But also the last thing is the binding energy that's maybe troubling here, because there's different ways in which the binding energy can be calculated and actually give sometimes a factor 2 or 3 differences between these methods. So if different projects assume different binding energy, you might find different alphas, or you might find different tendencies in alphas just because of the relation that you assume for the binding energy. So I think this is something to be careful of as well. Now, if I just summarize the studies that I found so far that constrain common envelope evolution in this way, that try to put a value at it, I found these 6 papers. And, the one thing that immediately strikes me when I look at this is, are these results discrepant from one another, or are we just looking at the uncertainty in the method, or are we just looking at the alpha common envelope prescription just not being adequate in prescribing what happens? And I also want to highlight these 2 studies from Ursula De Marco and Phil Davis that didn't try to find a single value for alpha, but tried to look at the dependencies of alpha on stellar parameters, so we can test these functional forms. So at that moment, this was still hard from small number statistics, but can we, make progress on this in the next few years with these larger samples? So also, what can we expect for white dwarf main sequence systems? That sample is already very large, might not grow very much anymore, but with Gaia, does the situation improve for double white dwarfs, for example? And how does it improve for SDB binaries? Okay, we go to the next slide. So the other method that is used a lot, and that I'm sure Ashley is going to talk about in a little bit, is the binary population synthesis method. So here we do not calculate backwards in time, but we calculate forwards in time. So typically we start at the main sequence, and then we follow the evolution of binaries in time, taking into account all of the relevant processes such as mass transfer, stellar evolution, angular momentum loss, gravitational wave emission, all these things. Now we do this for a population of binaries, and what we get in the end is an idea of what the demographics are of that population. So here you see an example. So this is what are the typical masses, the periods, what are the space densities, but also what are the rates of mergers or supernovae, for example. Now, this population synthesis method has been used to study many, many different types of binaries, and a good fraction of these projects also focused on trying to constrain common envelope evolution itself, besides using it, trying to constrain it. So here I just mentioned a few of them. And I just want to highlight this last population because it's showing, so this is the population of white dwarf main sequence binaries that come from Sloan. And I think this just shows very beautifully what the power is of a large homogeneously selected sample where we understand the selection effects very well. So these white dwarf main sequence binaries, if you look at the periods, these points here are the observed points, then we do not observe many sources with periods larger than 5 days. So of course this was known for a while, but before Sloan, it wasn't clear if this is a selection effect. And by having an automated survey like Sloan, you can actually study those selection effects, and it became clear that this is actually a real thing. Now, it is a problem because population synthesis, as you can see here, has always predicted periods that range up to hundreds of days. And so we try to look into this, take into account all the other selection effects, the color selection effects, but there's really only one thing that affects this, and that's how much you shrink during the common envelope phase. So if you want to express this as an alpha common envelope phase, it means alpha is smaller than we typically were assuming before that. If you don't like alpha, then just take it as the orbit is shrinking more than that we typically used to assume in population synthesis. Now, one more thing that I want to mention here about these white dwarf main sequence binaries is their cousins. Because a bit of progress was made very recently here, actually this summer. And the cousins that I'm talking about here are systems that have a white dwarf and a dwarf carbon star. So these dwarf carbon stars, or these binaries, we only have a handful of objects, and they typically have periods of several years or just several days. And those ones from several days, they are just really spot on with that population that we got from Sloan. Now, what is different between these main sequence stars and the dwarf carbon stars? The difference is that these dwarf carbon stars have a lot of carbon that they have accreted from their companion star when that companion star was a very evolved star. But the estimates for how much these stars would have to accrete in order for us to observe them as carbon stars is of the order of a few hundreds to a few tenths of solar mass. That is large amounts of mass during the common envelope phase. So with Ben Rolston, we were contemplated, does this mean that these sources can accrete during the common envelope phase, or are they accreting this matter before the common envelope phase? So in the process leading to the common envelope phase, possibly through a wind wash slope overflow scenario. So what can we learn about accretion during the common envelope phase? That is one of the other question points that I wrote down. Now, the last part that I want to mention here is multiples. We talked about multiples a couple of times during this conference so far, but I just want to highlight one aspect, which is I really want to hone this down, that they are more abundant than that they're often are being given credit for. So if you look at massive stars, then massive stars are very rarely found as single stars, very rarely found as binary stars, and typically triples or even quadruples. Now, if you go to solar mass stars, it's less extreme, but we still see that for every 3 binaries, there is 1 triple, 3 in 1, right? That is not negligible. So I kind of feel like I want to even that scale from us just ignoring triples completely towards saying, well, 1 in 3, that's not a super uneven scale. And I even want to go one step further. And that is because triples interact a lot more often than binaries. So what I mean with that is if you look at a triple population, then about 2/3, 3/4 of them will experience mass transfer at some point. However, in binaries, in the same mass range, it's about 1/3. Right? So if 1 in 3 systems or 1 in 4 systems is a triple, but those triples interact 2 to 3 times more often, then if you're interested in something that needs that interaction, these scales are actually pretty much evening out. So if you wonder where this number 2 to 3 is coming from, then this is coming from triple population synthesis. And of course, I want to give credit to the full team of TRAS that we're doing these simulations with. So TRAS is a stellar evolution code, population synthesis code that does triples So we're taking into account all of those processes that you used to for binaries, but also doing the three-body dynamics on top of that. The last aspect I want to say before I stop is that, so we find that this mass transfer is very common in triples, more common than in binaries, but we also find that when the mass transfer starts, that the orbit is very often still significantly eccentric, right? So here you see that in total, 40% of the mass transfers start eccentric. And if you look at giant branch stars, then I would say, what is this? Roughly 1 in 4, 1 in 3 starts with an eccentric orbit. So this is really showing you that there is a new framework that is needed for modeling mass transfer in these eccentric orbits and also eccentric common envelope evolution. So the question that I want to pose for that is, what are the roles that multiples have in common envelope evolution because they're common and because they interact so frequently? And how does the common envelope change for these non-circular, non-synchronized systems, or even when there's a third star close by? And lastly, can we recognize these eccentric common envelopes observationally? You know, is there some smoking gun that, or what are the smoking guns that we can use to find them? So I am going to finish with this, just a little summary of all those question points that I wrote down. I think we can take a few minutes for questions and then maybe leave a larger question session at the end of this session. So I'll stop sharing my screen. And I see 2 questions in the chat, and I'm wondering if somebody could help me with the questions on Slack, because I still need to open that. So I see that Enrique added a reference so this I think is X-ray binaries, where I'm guessing one of these methods, so probably the calculating the evolution backwards in time, had another constraint on alpha lambda. Yeah, just 1 point. So if somebody has a question, feel free to raise your hand. If there's something on Slack, please help me out for the moment and mention them.
There's nothing on Slack yet, but there's Great. Some raising hand.
Stephen.
Hi, Sylvia.
Hi.
I was wondering, when you simulate the evolution of these triples, how many of them actually end up surviving mass transfer as triples that would be observationally different from kind of normal common envelope binaries?
So that's a good question. But because 40% of them start in an eccentric orbit, you're kind of asking me to predict something that we're not really able to simulate yet. Right, so that's one of the reasons why you really need to be able to find a framework to model eccentric mass transfer. So I would say we don't have an answer yet, but give us a little bit of time, because that's definitely one of the things that we want to be able to answer.
Okay, thanks.
Alexei?
Yeah, thank you for the interesting overview. I'm curious about these triples. I mean, like, yeah, they come into this eccentric orbits and interact and possibly enter common envelope. So the question is, like, so if you take 2 stars on circular orbit which enter common envelope, the question is, will they always enter common envelope if they're on an eccentric orbit? In other words, does the critical mass ratio for common envelope depend on eccentricity? What would you feel?
I actually think that would be a great discussion point, or maybe something that Hila or Hagai have thought about. I see Hila switched on her camera.
Yeah. So the eccentricity will also change, like, the pericenter position. So and that's have a great effect on whether or not it will initiate the common envelope. I would say that probably if the eccentricity is very high, it can avoid a common envelope, but I don't know if it will cause a binary to enter a common envelope if with a zero eccentricity from the same pericenter at the onset of the common envelope, it will.
There must be something related to how deep you penetrate into the envelope.
Yeah.
Remember, like this work from several years ago from Melvin Davis, I think, looking at interactions in stellar clusters where, a star pretty much passes through the outskirts of a giant. Of course, that's a different orbit, but you just strip away a bit of the mass and then the star leaves happily and you get a partially stripped star. So could that be like a different starting point of a common envelope where you have a couple of these fly-throughs before you capture the companion inside of the star completely?
Exactly, and we also see that if we have a very high initial eccentricity, then we lose a lot of mass before the onset of the common envelope. And there's actually another question on how you actually define the initial parameters of the common envelope itself, because you don't have the same initial eccentricity, you don't have the same mass anymore.
I see two more questions. Unless I'm cutting you off, Hila. Were you still trying to say something?
No, thank you.
Okay. So Stephen, do you want to ask your question?
A couple of naive questions, if I may. What happens if the orbits aren't coplanar? So in the process of merging, you're going to generate higher order modes in tides, and if they're not coplanar, as in a couple of triple systems we know rather well, among which is Algol, you could excite gravity modes that could be strongly dissipative, and perhaps this is going to change the evolution. And when you've done these calculations, you've been assuming that the orbits and the triples are coplanar.
You mean in the triple population synthesis or in the eccentric common envelope simulation from Hila?
Both.
Yeah, so in the triple population synthesis, we assumed an initial random distribution of initial inclinations. And then we take into account the three-body dynamics.
And you've done the three-body calculations to look at the evolution of the orbit over time?
Yes, we did. Yeah, based on the secular theory. Yeah.
Okay. Thanks.
You're welcome. Ursula.
Hi. So going back to the question Alexei posed, if we don't expect crazy orbits like in clusters, but you can expect that gently this elliptical orbit will start at periastron to transfer mass. And the question I have is, would that change the orbital parameters in a way that would then promote the common envelope to happen compared to what it would have been if the orbit had been more circular? So the fact that you're just at mass transferring at periastron, but periodically, what does it do to the orbit that perhaps was happy just before mass transfer was taking place, but now it's different? So that would be, again, would that promote the common envelope in addition to the mass ratio usual criterion?
So the few works that have been about eccentric mass transfer have been about stable mass transfer. And sometimes the eccentricity decreases, and under other assumptions, the eccentricity increases. But I think in this respect, tides are very important, right? In standard binary evolution, we've kind of always been very simplistic about tides, saying that, the orbits circularize before the onset, and then we kind of don't have to worry about tides anymore. And that's no longer the case here. Now, if you ask me about the onset of eccentricity with the common envelope and how that is going to affect whether or not it's stable or unstable mass transfer, these are really good questions. But
yeah, and I think the tide will be dynamic. And if you do it in simulations, the orbit decays very rapidly if you have any mass transfer, but that's probably in great part a numeric thing, right? The orbit will decay less rapidly if you have higher resolution. So you have to be a little bit careful in making a judgment with that.
Yeah, that's a good point.
Thank you.
Okay, let's do the final two questions and then go to the other speakers. I feel a bit weird chairing this, so Karan, go for it.
Hi, Sylvia. Thanks for the overview. I've seen a lot of work around the low mass binaries, but since I come from the massive star observational side, so it's quite a far reach. So I was wondering if would you be able to extend any of the results that you have from your population synthesis towards higher masses, or would that be a whole different ball game and you would need a lot? There would be a lot. I know there are a lot more challenges, but would there be something drastically different?
There's one thing that changes as we go to more massive stars, so neutron stars or black holes, which is at some point you get a supernova kick. And that has two things. It makes it tougher to decide what happens with the orbits because there's an additional effect, plus many binaries then dissolve, so you have a smaller sample to work with, besides the fact that the IMF is already against you. So, not impossible, but it's just harder to do it for more massive stars for this reason.
All right, thank
you. Agai.
So I have two questions. One, what would actually population synthesis modelers would need from common envelope modelers directly? What would be the most important things? So that's kind of a question for all population synthesis studies. And the kind of reverse question is, what do we need from population synthesis? There are many things we need from that. I was just recently interested because of our work on triples on, for example, how many systems begin with a deep impact, but they start highly eccentric really, but inside the star. So this can happen, for example, from compact object, get a kick and are thrown into the other star. So that's one way. Or in some cases, triple stars can lead to very high eccentricity, which enter into the star, not just eccentric, the overall eccentric, but the pericenter is kind of the edge of the star. So I was wondering, because we studied both cases, we thought that the second case where we have deeply impacting cases would be more rare, but it would be interesting to actually know or quantitate it from population synthesis to some extent at least.
Yeah, I think some of these, I want to give the floor to the other PopSyn people as well, so feel free to add. I think some of these things that you mentioned, like what are the typical parameters that we expect for the stellar systems at the onset of the common envelope, for the triples, for the binaries, of course, I think population synthesis as a field has always been very happy to supply those. I can hardly speak for everyone, but if I would say, what do I want most? And I want the largest, most beautiful stellar populations to constrain my models. I'm actually happy to find something that's against my models because, that's when we're learning something. And from like the hydro side, I think it would be really great if we can maybe brainstorm about alternative prescriptions besides alpha common envelope, just like functional forms that we can maybe try out and see what the consequences are for these binary populations. Because I think pretty much everyone agrees that alpha is not ideal, but and a little bit of a criticism against PopSyn, but like what else can we do? So can we maybe like step on from that and come up with something?
So I'd like to just add something to that. And asking about what population synthesis people might benefit from or what we would need from modelers. So one thing that I find in my population synthesis simulations is, and I mostly work on type 1a progenitors, and often what's a very important phase for those and double white dwarfs in general is a common envelope phase that happens when the companion has already lost its hydrogen envelope. So it has a helium-rich envelope. And so you have common envelopes happen in this sort of helium giant phase. And I don't have a good, I don't know how different the common envelope would be. Maybe there's not much difference at all between having a sort of regular giant and a helium giant, but I know there's so much to do already on the 3D simulations or any dimensional simulations of common envelope, but including some that would involve these types of stars, And I know there's a whole lack in modeling low mass helium stars in particular. That would be something I would be very interested in.
Good point. Do you want to put up your slides, Ashley? Then we go to your talk. If other BPS people
sure.
Add their wish list, then so.
Okay. Okay, can you all see my slides?
Yes, we can.
Cool. Sylvia, will you give me a 2-minute warning just in case I need
Yes,
it?
I will.
Thanks. Okay. So thanks for coming, everyone. I'd like to thank the organizers also for accommodating my rearranging my talk time. Yeah, so I thought I'd talk about something a little bit different than what I normally work on. So those that know me know that I primarily usually work on progenitors. I'm trying to find progenitors of type 1a supernovae, various formation channels through rapid binary evolution population synthesis. I just want to talk very briefly about my institution, since I think many people have never heard of it before. So I'm at the University of New South Wales in Canberra, Australia. So that's the capital there. Yeah, so we're a pretty small group of astronomers. I'm happy to say that despite our borders being closed, I finally have 2 PhD students that just started working with me remotely from other continents. And Nicholas Rodriguez, actually, he's a registrant from this conference, so you might see him pop on later. Different time zone than me, so we'll miss each other. Yeah, and also just in Australia right now, there's quite a large interest in transient astronomy in general. And so I'll talk a bit about these interesting transients, these red giant mergers a little. But yeah, we hopefully with some government funding in the next couple of years to work on this in a more holistic way from all sides, from observations and theory. Okay, so yeah, so basically, so I work in, as you may have gathered, population synthesis. So of course, this is a very useful tool for figuring out relative rates of, or rates in general, birth rates of different types of events that you might be interested in studying, and figuring out their evolutionary pathways, and potentially ways to try to figure out ways we might be able to observe these different types of systems. So the figures I'm going to show today, so I made these in using Star Trek, which is one of the many binary evolution population synthesis codes out there. Wait, yeah, there we go. Okay, so just a little bit of what I tried to look at and what I had to look at in my models. So basically these results came out of a conversation actually that I had with a while back with Haggai Peretz. And so I was thinking about, what possible different kinds of transients might we be able to see with the upcoming Vera Rubin Observatory, otherwise known as LSST. Of course, I'm interested in supernovae and white dwarf mergers and things like that, but red giants are already quite bright. And so basically I was motivated through these discussions with Haggai to look into this with the code and see, how many sort of white dwarf, red giant pairs would interact and actually lead to some kind of merger. So either a double common envelope essentially, in most cases, is what's happening. Yeah, so the basic parameters of the simulation are there. So I've evolved close to 10 million zero-age main sequence binaries with different initial distributions for separation and masses, things like that. And essentially, I just extracted all giant-like binary pairs that do some kind of interaction. So have a common envelope event, essentially a common envelope between two giant stars, or a giant and a Hertzsprung gap, or 2 Hertzsprung gap. Okay, so Hertzsprung gap, right? It's just that phase in between main sequence and red giant. So it's as the star is starting to develop a convective envelope. So an early red giant, a subgiant star. So I wanted to look at these things. I should also note, I did look at numbers of AGB mergers and mergers on the horizontal branch, and those are there too, but I'm not talking about them today. They make up less than 10% of these. So I'm also just focusing on these sort of red giant-like systems. And so I find I put them in kind of two different categories. So there's what I call the double CE, where basically both stars on the giant branch or Hertzsprung gap essentially fill their Roche lobes at the same time and undergo this double common envelope. And then there's also mergers, and it's a little bit ambiguous, but at least in the code, what happens is essentially one of the stars rapidly fills its Roche lobe, and on very short time scales, the cores merge with each other. Okay, so there's this obviously continuum of things that might happen in between, but you have these basically really rapid mergers, or I guess that's some type of. I mean, you have an envelope there because it's a giant, so I don't know what you call them, but yeah, these are the two sort of categories of events. And in some cases, you end up with two surviving cores after the double common envelope. Actually, many of these, you have the two cores, the helium-rich cores survive. In the mergers case, they always merge together, okay? So I just want to show the delay time distribution of these red giant mergers. So I work on supernovae, so I often think in terms of delay time. So just assuming all the stars are born at t=0, you take a look at when the merger happens. So it's basically the age of the system when it merges. And yeah, essentially the delay time here is fairly flat, and that's just mostly a reflection of the fact that the majority of these systems occur from relatively low mass stars. So the peak is around 1 solar mass on the zero-age main sequence. So it's really the more massive ones that have these rather short delay times, less than a gig a year or something like that. Okay, so I want to show a figure now of the zero-age main sequence masses of these stars when they undergo these double common envelope merger things. I'm only showing you the plot for the primary. That means the most massive star on the zero-age main sequence. It's what I call the primary. Because it's confusing because if you're an observer or a theorist, you may have completely definitions of what primary means. But yeah, I call it the initially more massive star. So basically, the distribution for the secondary looks almost the same, not exactly, but by definition, because we're seeking out stars that enter the giant branch at roughly the same time, by design, they're going to have about the same distribution of masses, okay? So of course, because of the IMF, I'm using Krupa IMF here, the majority, well, not the majority, but a large fraction of them are going to have relatively low mass, so around 1 solar mass. But of course, we see some systems up to close to 10 solar masses or so. I only evolved up to 100 solar masses was my upper limit on the IMF. So that was for the zero-age main sequence, okay, for these stars. They evolved along. Now I want to show you a figure showing the masses that these stars have at the time of the merger or at the time of the interaction. Okay, so I'll explain this plot because it might be these plots might be a bit more confusing. So the primary masses are plotted on the left, and the secondaries, so the less massive star at time of birth, are on the right. So the blue shows this kind of double common envelope where they both fill their envelopes at the same time and often result in 2 surviving cores. In some cases, maybe they don't survive. I didn't have time to look at all those details. And of course, it really depends on, of course, which prescription for common envelope evolution you're going to use and alpha and things like that. But this is when they fill their envelopes. And then the ones that in my simulation do end up in a full-on merger, and it's fairly rapid, those are shown here in orange. So basically you can look at it like the blue stuff on the right and the blue stuff on the left, those go together, right? The primary and the secondary, and similarly for the orange. So there's clearly this interesting thing that happens. So there's this flip of mass ratio that happens on the evolution, during the evolution on the way to making these double common.
I think Ashley's Wi-Fi probably just went down. Am I the only one that doesn't hear her anymore?
No,
Yeah.
she's gone. She's gone.
I just wanted to give her the 2-minute signal, but she took that very fast.
Maybe we
She'll
can
be back.
address some of the questions in Slack. I don't know, Sylvia, if you managed to open Slack for yourself.
I open it now.
Okay,
So yeah, indeed, if you have questions for Ashley, let's put it there. I think in the meantime, we continue with Stefania's talk. Hold your questions to Ashley, and maybe at the end, Ashley will, log back on and can give the summary of what she was still trying to say at the end of her. Oh, Ashley's back. We cannot hear you yet, Ashley.
Sorry, thanks. I'm using my hotspot now, so hopefully that doesn't happen. Let's see. Should I?
Yeah, just continue. I was just about to give you the 2-minute warning.
Okay. All right. There we go. Okay. Sorry. Did you see this figure yet?
Yeah, we did see. Yeah.
Okay. Yeah. So basically, there's a mass ratio flip that happens. So during the evolution, basically what happens is as the stars start evolving, the primary evolves off the main sequence. It will fill its roche lobe first, right? Because it's slightly more massive. It'll dump mass onto that companion. And both companions, of course, they're evolving. Eventually, they end up either as both Hertzsprung gaps or both red giants, or one's one and one's the other. And that secondary ends up being more massive than the primary. And eventually, they end up merging. So filling their envelopes at the same time. So this is my really fancy sort of evolution view of a little cartoon of sort of a typical system. And this is basically what happens. And in this particular case, you end up with 2 helium-rich cores. So I wanted to just briefly show a nice figure that Hila recently sent me. So essentially, I gave her some initial conditions for a binary from Star Trek, a typical case of one of these mergers. And she evolved these stars basically with Mesa, with some mass loss, and mapped them into Gadget. And this is just this is much nicer than my little cartoon there. So I thought I'd show that. Yeah, but hopefully we can look into more detail at these different types of systems. Mostly, they of course happen pretty low mass. We might expect a few of these things in the Milky Way now, but I'll just leave this slide up because I know I'm probably out of time. But of course, that was just an estimate for the Milky Way. We're interested in actually detecting these things with Vera Rubin because they're already going to be giants or on the way to being giants before merger. They're already going to be fairly bright compared to, say, our typical white dwarf merger progenitor. Yeah, and of course, what do these things make? That's another interesting question. But yeah, I'll stop there. Thanks.
Thank you, Ashley. I will invite anyone to raise their hand if they have questions or to put it in the Slack. And Haggai has had his hand up the entire talk. So either he was very eager to ask a question or it was from the previous one. So I'll go to Aldana. Yeah, and then Haggai took his hand down. Do you want to ask the question?
Hello. Very nice talk. I want to ask you if I understood correctly. Most of the binary masses are very low due to the initial mass function. So I wanted to ask how more complicated would it be to apply your code or simulations to the populations of massive stars?
Sorry, you're asking. Sorry, I just didn't hear the last sentence about massive stars. Could you repeat?
Yeah, First, I wanted to ask why all the masses and simulations were low. You focused on low masses, or is something the simulation gave you?
Oh, it's just out of the simulation, because we try to emulate nature, right? I mean, as best we can. And so using the IMF, this is what comes out. Statistically, we just expect more of these red giant mergers to happen at lower stellar mass. Yeah. I'm just going to stop sharing my.
Okay, thank you.
Yeah.
If there are no other questions at this point, then I will ask Stefania to put up her slides. And I can maybe ask a quick one to Ashley. which is if you use this alpha common envelope prescription for this double giant common envelope, then one of the stars is not filling their rush lobe at the onset of the common envelope phase. So probably that star very quickly would swell up based on all of this matter that's coming to it. But then how do you calculate the binding energy of that secondary star? Should we be worried about that?
Yeah. So basically in that simulation, so I had a few different runs. So we used the modified fits of the Zhu and Li paper to estimate what lambda would be. So based on the evolutionary state of the donor. So the binding energy is basically wrapped up into the lambda that we would get from the estimate from whether it's a Hertzsprung gap star, etc. But yeah, I do. I'm also
like an unperturbed star in a way.
Right. Yes. And so this is not. I mean, this is not the most ideal way to treat it, of course. And I think. This is definitely something that I agree. This alpha prescription simplified way of looking at common envelope, it really isn't good enough. As you say, it's kind of like, well, it's what we have to work with to be efficient at what we're doing. But yeah, that doesn't necessarily mean it's the best way forward. I don't think it is.
Maybe another thing to put on the wish list that you make us think of, that's something to think about.
Yep.
How does the giant respond? Okay, then I see there's one more question from Morgan. Maybe you can put that one in the Slack and Ashley can have a look. And then for now, we go to Stefania Hernandez, who's going to tell us all about white dwarf observations.
Right. Hi, everyone. Thank you for the opportunity to give the talk here. Today I will talk about the white dwarf binary pathway survey, and this survey is dedicated to the study of post-common envelope binaries with interstellar mass stars. And our goal is to characterize all those binaries that, to obtain the constraints to calibrate some of the uncertainties for the binary population synthesis, and also for the searching for the supernovae 1A progenitors. That were shown before, this is the big picture of the evolution of a binary system, starting with two main sequence stars with intermediate mass. And as always, the more massive will evolve first. When it is in the AGB phase, it will start to transfer mass in a dynamical and stable way, and will cover the entire binary in a common envelope. When the common envelope is ejected from the binary, they take angular momentum with it, resulting in a closer binary, call it post-common envelope binaries, that are formed by the original main sequence, one of the original main sequence stars, and now the evolved core of the other star that it's now a white dwarf. What will happen next will depend mainly on the orbital period of the of these post-common envelope binaries. And for example, for long orbital periods, these binaries will have the time to evolve into a second common envelope phase, and we will have a result double white dwarf binary. What will happen after will depend mainly on the mass of this white dwarf. And for short orbital periods, then we have some other options that mainly depends on the evolutionary state of the secondary star or the main sequence star and the mass ratio of these systems. We can experiment, or we can show binary evolving into stellar merge or super sources and probably supernovae 1 explosions, or the cataclysmic variables. In this survey, we dedicate our study of the post-common envelope binaries with spectral types A, F, G, and K secondaries. And as these binaries are quite difficult to detect because the secondary star it's completely outshine the white dwarf in the optical. We combine optical observations with ultraviolet observations from galaxies and selected all those A, F, G, and K stars that shows ultraviolet X's that are shown with the blue points or blue dots. And after observe them and confirm the binarity, I perform follow-up observations with high resolution spectroscopy, measuring the radial velocities to measure the or calculate the orbital period. I selected 5 of these binaries that are shown with these red stars and characterize them. These binaries are shown here. Well, they were selected mainly because all of them have G-type secondary star. Only one, the blue one, have a K secondary star. And the orbital period of these systems are all between 20 hours and 2.6 days. After obtain the orbital period and the stellar parameters of the secondary star, I estimate the white dwarf parameters. And I want to say that for these two systems, we we observed they have these observations, and we study. What is it? We study the light curve, and we detect they have secondary stars very active, showing flare activity and star spots. And we saw a clear difference between these two systems. One of them have star spots that are changing over the epochs, and the other, and you can see it in these two plots, and the other have long-lived star spots that are migrating over the surface of the secondary star. All of them, these two systems were confirmed to be tidally locked, but we observe as slightly different between the orbital period and the photometrical signal of Tycho 110 of 18 minutes. And we explained this with the differential rotation in the surface of the star. Also for Tycho 110, we obtain HST observations among other 13 stars, if I remember well. And we could confirm the presence of the white dwarf in this binary. Also, we obtained the precise mass of the white dwarf, and also we saw that it shows emission lines in the optical and the ultraviolet that are related to mass transfer. And with X-ray observations, we couldn't confirm this, that it's actually happening, the mass transfer. So we conclude this emission lines may be produced by the activity of the secondary star. With the with the parameters of the binaries, mass, radio, orbital period, and metallicity. I perform MESA simulations. Of the system, of the 5 systems, and what I show here, it's with the lines, the stability limits for different type mass transfer. And what I discover is that 2 systems marked in green will run into dynamical unstable mass transfer, and then they will enter into a common envelope, but the energy to bind the binaries will not be enough. And they will evolve into, well, they will experiment at stellar merge and evolve into a single white dwarf. Other 2 systems in red, 2 minutes. Other 2 systems in red will evolve into cataclysmic variables with evolved secondary stars due to the secondary star in those binaries. Right now, it's a bit is slightly larger than a main sequence star, C-range H main sequence star. And in these binaries, the secondary star will not convert fully convective, and the mass transfer will not stop even during the 2 to 3 hour period, orbital period. And the last system that I observe will probably enter into a supersoft phase, but will not reach the Chandrasekhar mass to explode as a supernovae. So it will evolve into a cataclysmic variable. Also, we have I did the orbital period distribution and compare it with the main sequence, with the post-common envelope binaries with M-Dwarf. And we saw that for these more massive post-common envelope binaries have or can identify 2 populations, one with short orbital period and one with long orbital period. And if we compare this with models, with population models, we saw that the binaries with intermediate mass evolve or can be explained, their evolution can be explained as the same as the post-common envelope binaries with M-Dwarf. This means they use the same alpha to bind the binary, but those binaries with long orbital period need some extra energy to bind the binary, or they simply escape the common envelope phase and experiment a stable non-conservative mass transfer. And if we confirm this by the more observations of long orbital periods systems, well, this can be representative or have a impact in the production of supernovae 1A through the double degenerate channel. And I will leave just the conclusions here to you can see them, and I will be happy to get your questions.
Thank you, Stefania. So I'll invite everyone again to raise their hands if they want to ask a question to Stefania, as well as put it on Slack. I already see a bunch more questions for Ashley have come up in the Slack, so it's great to see that. I see a question from Laura.
Hello, thank you, Stefania. I was just wondering what you meant when you said you thought it might evolve into a super soft source rather than a CV, like what the difference between those 2 evolutionary paths is.
Oh no, I mean, here, it will be a super soft source by a short time. This means it will experiment thermal unstable mass transfer, and will the white dwarf will increase its mass, but then it will evolve into a normal cataclysmic variable with a slightly massive white dwarf.
But what's the difference in the companion star between that faster evolution and the CB evolution? Is it
in this one? Well, it's mainly because the mass ratio of this binary that will happen that, but in this binary, the radio it's of the secondary star is mainly the same of a 0H main sequence star. In the others, the radio is a bit larger. This means the secondary star in this moment, they are a bit slightly evolved.
I see.
Can I just mention, I think because of the mass ratio, for example, that would also affect the rate of mass transfer, which I guess to say achieve like efficient accretion on the white dwarf, you usually need to be assumed within a certain sort of mass transfer regime, and that can only readily be achieved with certain combinations, for example, of a given white dwarf mass if the donor has a certain mass. So
cool. Thanks.
Okay, Stephen had a question as well.
Stefania, on one of your slides, I think the one after this, you had shown QIC 110, that's it, and V471 Tauri. How do those, you've got enough phenomenology now for these systems. How do the two of those compare? Because V471 is a really neat system in that it's an RS Kanban type system. It has large star spots, it has activity. There's no evidence of mass transfer. And if I remember, the temperature of the white dwarf is about double what you have.
Yeah.
The orbital period, I think, is a half day. But otherwise, have you followed DYC 110 long enough to do a comparison between these two? Since you said it doesn't show X-ray and 471 does, but it's corona.
Yeah. Well, what we mean here is that this short orbital period of systems can be evolution can be explained with the same unbinding alpha as the main sequence star does the post-common envelope binaries with M dwarf. This is 0.2 to 0.3 alpha. But compared with these long orbital periods systems, for example, COI 3278, they need this extra energy. But this is what you ask, or?
Well, the specific reason I was asking is that there's enough known about V471 that it might be a good model system for some of the ones you have in the short period in kind of this intermediate mass range to get an idea of what it is you want to finally reach. I mean, there's much more known about that system for a longer period of time. It's been observed for like 30 years than what you would have for 110 and perhaps C760.
Perhaps I can ask to continue the conversation on Slack. Really interesting, but maybe for time we should probably go there. And I see two more questions. Please put them on Slack or keep them until a bit later in the session. And then I think it's time that we go to Avishai's talk.
Should I stop sharing the?
Yeah, if you could take your slides down.
You don't want to make a short break, even 5 minutes?
We can do that if you guys want. I prefer having like the full hour break between this and the next session, but whatever everyone's up to, whatever everyone wants. I kind of like this style.
According to studies, kids have problems sitting a long time in front of the Zoom. They didn't do the experiment with old people, but kids cannot stay 2 hours. If you think 10 minutes is too long, I suggest 5 minutes, but let people prepare coffee or something. I don't know.
Then let's do a 5-minute break and reconvene at 10 past the hour in whichever time zone everyone's in. So then if we're recording, then let's get started with the second half. And Avishai Gilkes is going to take us to the more massive end. He's going to tell us about neutron stars. Take it away.
Okay, thank you. My name is Avishai Gilkes. I'm a postdoc at Tel Aviv University currently. I would like to thank the organizers for the opportunity to present this, which was done with the collaborators listed here. Especially, I would like to mention Alex Tanaka, whose master thesis project was the start of this work, while both of us were in Cambridge. So a lot of the work I'm presenting was done by Alex during and after his master thesis study. So I will start with going to the bottom line, just showing the main result, and I will then go back and explain how we got this. So we calculated using a rapid stellar evolution code and a population synthesis approach, the rate of merging neutron stars that we should detect locally. So this is the rate density, the rate per unit volume. And we can compare this to what has so far been measured by LIGO. So if we look at this plot, we can see the results from many different calculations with different parameters. Especially, we focused on the sensitivity to common envelope physics and supernova kick velocities. And what we can see is that there is a very large sensitivity to both of these. So we have a computed rate, which varies by orders of magnitude, depending on our assumptions on what happens during common envelope and during the supernova. And the title, we say that we have this optimal efficiency, which is just saying that there is a maximal point as function of alpha. So it's not that the process optimizes to give us a large rate of merging neutron stars, but it's a result of different processes, which I will explain in more detail later. So we used Rob Izzard's binary C or rapid evolution code to simulate many binary systems. And the key physical ingredients are listed here. These are not all of the physical processes, but some of the more important ones are star formation rate, initial conditions, different distributions for the masses, orbital periods, mass ratios, and metallicity. And the two things that, as I mentioned, we focus on are the supernova kicks and the common envelope ejection. And we focused on the kicks of electron capture supernovae. So we treat kicks differently for core collapse from iron core or from electron capture. And we keep the kick velocities for the core collapse constant and focus on the electron capture supernova kicks. And in our simulations, the electron capture supernovae are the dominant formation of the merging neutron stars. So the simulations range many different values of alpha, the efficiency of utilizing the orbital energy to eject the envelope, and the values range from 0.05 up to 10. And we also changed the electron capture supernova kick velocity distribution with so we use a rather simple distribution, a Maxwellian distribution, but we have a different dispersion. So we have either zero kick velocity or some dispersion with different values, most of them low, but also a high kick velocity of 265 kilometers per second, which is the velocity dispersion that we assume for the core collapse supernovae. So we have a total of 75 different combinations of the common envelope ejection efficiency alpha and the electron capture supernova kick velocity dispersion sigma. And for each of these 75 combinations, we have about a million systems simulated for the different metallicities, orbitals, separations, masses, and mass ratios. The masses are focused on the higher masses, so we ignore all of the most of the lower masses because we are focused on systems which result in double neutron star formation. Okay, so now for some results. So here we see the number of double neutron star systems which are formed in several grids. So this is for the highest metallicity, 0.02 that we ran, and for 4 different kick velocity dispersions. And what we can see is that as a function of the ejection efficiency, we have more double neutron star systems formed. And this can be explained, I think, rather intuitively, and as the ejection efficiency is higher, then more systems which enter the common envelope will survive as binaries. So for a very low ejection efficiency, the common envelope will not result in a binary, but in the neutron star merging with the core, which can either form something new or an explosion or something like that. So the main, I need to mention that the main channel here for these systems to form is that the first neutron star formed before common envelope evolution happened, and the first common envelope phase is when a neutron star enters the envelope of its companion. Okay, so we see that this increases monotonically with alpha. Now, if we look at only at those systems which have, after they form, a time to merge shorter than the age of the universe, then we see that for the higher alphas, the numbers drop. So what happened here? The higher the alpha value is, then the separation after the common envelope will be larger. So for very low alpha, because the envelope ejection is inefficient, the neutron star needs to plunge further in to release more energy, so we will have envelope ejection. So for low alpha, we have small separations after the common envelope. So actually this peak at the alpha of about a third here is a result of 2 different processes. One is, as we increase alpha, we have more binary neutron star systems, but also their time to merge becomes longer. So we have 2 opposing processes, and this results in this optimum. Why is there a second rise later on? So I think that there might be another peak, and the reason is that we have different channels. So when the neutron star enters the envelope of its companion and we start the common envelope phase, then the companion can be different types of stars. So we have, if we decompose this and we look what is the type of star that is involved in the common envelope phase with the neutron star, then we see that the first peak is a result of stars which have convective envelopes, and the later rise is from stars which are, for example, Hertzsprung gap stars, which has a different structure. And actually, in one of the metallicities that we ran, the lowest metallicity, we did see a second peak at alpha of about 5, and there might be this second peak also for other metallicities, which is either at an alpha of above 10 or it's somewhere here between 5 and 10, but we didn't sample enough values.
2 minutes.
Okay, so what actually happens is that we have for a low alpha, most of the systems that form will merge because they have short delay times. And for larger alphas, we have more systems, but the fraction of them that will merge within the Hubble time becomes much lower. We can see this in these probability distributions of the delay times. So we see for the low alphas that we have most of the systems with short delay times, and as we increase alpha, the delay times increase. And we have the short delay times appearing again for the second channel of forming double neutron stars. And now we take these numbers of systems from the grids and compute a rate using some star formation history and metallicity distribution to combine the different metallicities. And this is the plot that I showed in the beginning. So, and again, decomposing this for one of the kick velocities into different channels, we can see that we have this dependence on the channel. And we have in the bottom line, what we have is a very large range in the computed rate, depending on the envelope ejection efficiency and the kick velocity as well, because higher kicks will disrupt more systems. And the bottom line, I think, is that we are very sensitive to common envelope physics, even if the alpha prescription is not sufficient. And we know that it might be more complicated than this simple prescription. This using alpha can help us to understand how important the envelope ejection efficiency or the envelope ejection process might be for the formation of merging neutron stars. And we have from these computations computed rates which are either higher or lower than the limits of given currently by LIGO from just a couple of neutron star merger events. Okay, so I think I'll stop here and see if there are questions.
Thank you, Avishai. I see a couple of clappings. Yeah, again, I invite everyone to ask a question or to raise your hand. Give everyone a second to do that. Otherwise, I have a question for Avishai. Okay. That's, what would it take in order for us to turn this around and to use the gravitational waves in order to constrain common envelope evolution?
So I think it's a bit of a problem. If you can make this thought experiment, you narrow the range from LIGO and make it we have a very good estimate of the rate. You can still have a multi-valued solution for alpha because you can have the same rate at a low and high alpha. But I think that this misses the point that maybe the alpha prescription is just not good enough, and we might need something better. And maybe with a better prescription, which is more, which includes more physical processes, or based on updated simulations, maybe then we could use these to constrain the process.
Thank you. Alejandro, do you want to ask your question?
Yes. Hello, Avishai. Thank you. So these results are very familiar for me because I kind of been working on these two for a few years now. And I was wondering if are you thinking about comparing them to what other codes have already done? Because from what you described, that I think it was described in a very clear way, it seems that this is similar to, for example, what Nicola Jacobo using MOBSC kind of explored, and also what we in Compass explored. So I'm not sure if it actually is as similar as I am imagining, or if it's not that similar, and if you're gonna thinking about comparing them.
Yeah, I think that one point which is interesting in what I showed is that is the high resolution of alpha at the lower values. in a recent paper by Santoliquido, that's Mappelli's group, they have also some different simulations with different alpha values, and I saw they have it in a table, not in a plot like this, but I saw that they have a maximal rate for alpha equals 7. So they have the rate rising with alpha, it peaks at 7, and for the higher alpha, they have a lower rate. So I think this is similar to our second peak. So yeah, comparing to other works is definitely very important. So we're working on writing the paper now, and hopefully we'll mention all the relevant previous works.
Thank you.
Okay, let's, Avishai, if you could take your slides down, and Karen, if you could put yours up, then Ryusuke, if you have a very good question while they do this, fire your question.
Yes. Have you tried to look into the rates of script envelope supernovae, depending on like the different alphas? Like the double compact object formation has lots of other uncertainties, so it might be more direct thing to compare with.
Okay, so the stripped envelope supernova is an important point. After the first common envelope event, which involves a hydrogen-rich envelope star and a neutron star, then afterwards the second star would be a helium star. So we would have the second neutron star forming in our channels from a stripped envelope supernova. We didn't look at the rates of stripped envelope supernova, but I think it's a very good point that this is something that that should be done to relate the neutron stars to the stripped envelope supernova, which might form them.
Okay, then let's go to Karan, who's taking our trajectory along the mass range further and further, all the way up to the very massive, the most massive stars.
Thanks a lot, Sylvia. Can you give me a 2-minute warning, just in case I tend to go over time? Thanks. So hi, everyone. Thanks a lot for coming to my talk, and thanks a lot to the organizers for giving me a talk. I've come from the far land where we take observations of massive stars, so quite far away from the low mass theoretical community. And as I just wanted to go back to Sylvia's overview, as she said that we are slowly overcoming these small number statistics. That will sadly not be the case for my talk, so please keep that in mind. And this work is done in collaboration with Hugues Sana and Thomas Chenard, among others. And I'm excited. So a little bit about the Wilfred phenomenon. So usually when stars with initial masses greater than 30 times the mass of our sun evolve, they are able to strip themselves via their stellar winds, or in some cases with the help of a binary star. And then they travel to the blue in the Hertzsprung-Russell diagram, where they appear as Wilfred stars. So these Wilfred stars have really dense and optically thick winds. So the optical depth of unity is formed in the stellar wind itself. And so the spectra that we see are emission line spectra. And as observers like to do, we tend to put stars in boxes. And depending on what we see in the spectra, we either classify them as nitrogen-rich or carbon-rich or even oxygen-rich Wilfred stars. And what we see in the spectra is thought to be a result of the nucleosynthesis that's happening in the star itself. So if we see nitrogen, it's because of hydrogen burning, and carbon because of helium burning. So naturally, when we look at these stars, you think, okay, so this is probably how they evolved. And then we come to the modified Conte scenario, which is one of the proposed scenarios for massive O stars, and as to how they evolve. So they can go from being an O star with perhaps an intermediate luminous blue variable phase to WN, WC, and if they're massive enough, WO stars before becoming a black hole. So we are quite familiar with the multiplicity of O stars, but we have but then we also have a lot of these black hole binaries that we see with gravitational waves. So the question is, what happens over here? What kind of physics are we missing? So a lot of the O stars that have been found, they have been found in binaries of with periods of the orders of days to hundreds of days. So there are very few binaries that have long periods, and this is sort of our starting point, and it's the starting point for a lot of population synthesis. However, if you look at an evolution of such a main sequence binary, you can have perhaps stable Roche-Loeb overflow and then a Wilfred star, and this is what we are looking at. So a Wilfred star that appears with either a main sequence O star, or you can have a Wilfred star with a compact object as you follow this evolutionary sequence. And this is just an example of what can happen. So knowing the multiplicity of the Wilfred population will give us constraints on these intermediate stages that are so far theoretical. And also understanding the distribution of periods and eccentricities will help us put constraints on what happens in sort of binary evolution. To what extent does the period change after mass transfer, for example? So in order to do this, we embarked upon a radial velocity survey with the Hermes spectrograph that has been mounted on the Mercator telescope in La Palma. And with from Paul Crowther's sample of galactic Wilfred stars, we got a sample of about 40 objects, as you can see, according to their different spectral types. We aim to get about at least 6 epochs of observations over at least 4 years. And we have quite a high resolution and moderate signal to noise. So it's high quality data, and we're hoping we can measure radial velocities of these stars. And what do I mean when we measure radial velocities? So this is just a toy model, so to say, of a binary system. And if you're looking at the Wilfred star, which is the primary here in yellow, as a companion, as it goes about its orbital motion, in the line of sight, it seems to wobble, come towards us and go away from us. And that directly causes the spectral lines to move in in velocity space, so the Doppler motion. And this is what we can plot as a function of time in a radial velocity curve. And so this peak, the amplitude, is what I measure with our survey. So we are focusing on delta RV, the amplitude of the motion. And as the mass ratio goes towards unity, so when both companions are of equal masses, then this radial velocity amplitude also goes up. However, if it's with a low mass companion, as you can see over here on the y-axis, the amplitudes that you see over here are quite small, of the order of a few kilometers per second. So here I'm just going to present results from a paper that we published last year, which focuses on the carbon-rich Wilfred stars. And over here, I've put the sort of modified Conti scenario as an evolutionary sequence on top. And you can see that these are the stars that are most likely, we are looking at them directly before they become black holes. And over here, so this is some sort of a threshold plot where, so where on the x-axis you have sort of a measure for delta RV, the peak-to-peak amplitude that you measure for these objects. And if they're in a binary, we can say that, okay, anything greater than 10 kilometers per second, if I see a radial velocity displacement, if I see a peak-to-peak value more than 10 kilometers per second, I can call it a binary. And that's our adopted threshold value. The names in bold over here are binaries that are already known. So in the literature, they've been studied. We have periods for some of them, and they're of the order of years, and with some of them, the order of a few days to a few months. So with So using Monte Carlo simulations and accounting for the small sample size, we were able to correct this observed binary fraction and sort of find a minimum value, a lower limit on the intrinsic binary fraction for galactic Wilfred stars. And we found that to be about 70%. But most of them, so we went back and did a literature study as well, because obviously a sample of 12 stars is quite small. And we found that most of them are in long period binaries. And there are very few, less than 10% of all galactic carbon-rich Wilfred stars are in binaries of the order of months. And so that is quite a stark contrast as compared to the main sequence O stars. And so this is a bit of a challenge over here, because usually when we think about common envelope evolution, we think about it when you already have a compact companion, when there's already been a supernova and whatever surviving system, that's when we look at it. But with respect to the formation of Wilfred stars, when you have mass transfer, does common envelope, do we see a common envelope scenario there or not? In order to look at that a little bit more in detail, we go to the WNE, so the early WN stars. And over here, so this is all work in progress. And over here, we have a slightly larger sample. So we have about 16 stars. And already you can see that the x-axis over here is quite different, an order of magnitude. So where you had delta RV values of the order of tens of kilometers per second, you have it here at about hundreds of kilometers per second, which directly translates to the periods of these binary systems, where they resemble more the main sequence O stars, where you have periods of the order of days to months, and a few of them of the order of years. We find a lower observed binary fraction, so 44%, and we actually even have one hierarchical triple system, since Sylvia was mentioning triples. So we have a Wilfred, which is in a wide orbit with an OB system. After performing some Monte Carlo simulations, we found that our intrinsic binary fraction for the WNEs is at least 50%. However, the period distributions are quite different. So we see binaries in much shorter periods, and we also have some initial simulations that suggest that the period distribution is not flat. And what does this mean? It means that we have a population of WNEs that are close, bright, and are at short periods. And we don't see an equivalent population of WCs that are also close, bright, and are at short periods. So if these binaries evolve, what do they become? Next, we see a population of super long carbon-rich Wilfred binaries, but we don't see their progenitors. It could be that we actually have a bias where we just don't measure their long periods and we need to monitor them extensively. So that's what we're going to follow up in. But the second point is sort of a main question mark as to what happens with respect to binary evolution. What kind of physics are we missing? Do these systems merge, or is there something else that happens? That's it. That's all from me. Thank you. And I'll take questions.
Thank you, Karan. Thank you for staying perfectly on time. That means we have ample time for questions. So if anyone has any questions that you want to ask Karan, I see one question already from Amit. Please go ahead and ask it.
Hi, I wanted to ask if you know anything about the eccentricities of those systems. Which of those have a large eccentricity?
So if I will just go back here. So for the carbon-rich sample, these two stars have non-zero eccentricity. So 0.9 for 0.9 or 0.8, I think, for WR140, and 0.3 for WR137. The short period system has a circular orbit. And if I go to the nitrogen-rich sample, most of these are in circular orbits, and the long period one has an eccentricity of 0.3, I think. Again, I'm not sure about all of the other values off the top of my head.
Thank you.
I see a question from Hagai in the chat, who is asking, what companions do these stars have?
So the carbon-rich Wilfred stars usually have late type O stars as companions. And there's also, so if I go back here again, so these three of them don't have confirmed periods, but they do have companions. So this one has a BE star as a companion. So this one, we don't know what the companion is, neither we do for WR146. But for these three, they are late type O stars as companions. And if I go to the WNEs, here you have a little more early type and some late type companions, but they are all O stars.
Thank you. I see another question from Ursula.
I don't have a good sense of the sizes of these massive stars, but if we take a simplistic approach and we assume that all WN stars have gone through a regular nice common envelope and become a WN star with a companion, and then we apply just some simple formalism, you could predict a period distribution of these objects. So what would that expectation be? Where would they be in this graph?
So if I take a population of main sequence O stars and then make them go through a common envelope and then have the WNs. Do I understand that correctly?
Yeah, because I was actually asking Ilya Mandel just the other day, do we have a nice clean sample of massive post-common envelope stars, just like we have for the low mass stars, that we can then use to do reconstruction type work? And he said, well, not really. But then he talked about the Wolf-Rayet binaries, and he said maybe that, but of course, every time you say Wolf-Rayet, it becomes complicated. But what would the expectation be if you had the simplest possible scenario? You'd expect probably short periods, but short in this scale, I don't know where they sit.
So I've been talking a lot about this with Pablo Marchand, and short in this sense would be the order of a day or less than a day. Yeah.
And you don't see that. You'd see
I don't see that. So there are some in the literature that have quoted periods of less than a day, but they are studies from the 80s and the data quality was not that great. So they really need to be revisited.
Okay, I'll ask Karen to take his slides down. Palmira, if you could take your slides up, and Alejandro, quick question.
Just a comment following that, because I think that the thing when you strip these stars, if they become WN, they might also not spend the whole time of their lifetime as helium stars, which is already very short. Let's say it's 10% of the whole lifetime. They only spend a fraction of it, and then they become WCs. And then also this division depends on mass. And then depending on where you put the mass division, your rates change a lot. So this post common envelope period distribution is not as straightforward as it could be maybe in other cases. But I think people are working on that. I know David Aguilera Adena is working on that, and probably Karen and Pablo also. So let's stay tuned, I guess.
Yeah, so the main, sorry, just 30 seconds on what Alejandro said. So the main challenge is that we are not quite sure how Wolf-Rayet stars form. So are they mainly formed by stripping themselves, or do they form in a multiple system, either a binary or a triple? So I think that's one of the main questions that also needs answering if you were to talk about post-common envelope systems. Thanks.
Okay, thanks everyone. And then we go to Palmira, who's going to tell us all about dust properties in these massive stars. Take it away. I'll give you a 2-minute warning.
Okay, thank you. Can you see my screen, right?
Yeah, we can see it and we can hear you good as well.
Hello, thank you for the opportunity. My name is Palmira. I'm the last year of my PhD, and my advisors are Jane Arthur and Jesus Toala. The title of my talk is Dust Properties in N167 and RCW58, Evidence for a Post-Common Envelope Scenario in Massive Stars. Okay. In a single star scenario, all stars with initial masses higher than 25 solar masses evolve into a red supergiant or pass through a luminous blue variable stage, in which the star experiences a dense stellar wind or eruptive mass loss episodes, respectively. Finally, after losing its hydrogen-rich envelope, the star exposes its helium-rich core, becoming a Wolf-Rayet star. The star is thought to end up its life as 1b or c type supernova. Wolf-Rayet stars can be nitrogen-rich, carbon-rich, or oxygen-rich. In some cases, there are nebular material around these stars. Here, I show you an example, RCW58 around Wolf-Rayet 40, and the upper panel shows the optical nebula and the bottom panel shows the infrared counterpart. Okay, mass loss is important at all stages of a massive star lifetime. It is known that Wolf-Rayet stars have a fast and powerful stellar wind, and although the O-type stars have a less dense stellar wind compared to Wolf-Rayet stars, but it is not negligible. Thus, the study of World-Rayet Nebula can provide information on the Maslow's history and previous evolution of the central star. In this project, we are looking at the evolution of the gas and dust properties in World-Rayet Nebula around WNH stars in order to understand the formation and evolution process of the dust around massive and luminous stars, as well as the evolution of themselves. The WNH stars are characterized by hydrogen emission lines. These allow to suggest that WNH stars are an intermediate evolutive phase between main sequence phase and red supergiant or LBB phase. In particular, we focus on WN8H stars. These stars are having considered as first stage of the WNH phase. In our galaxy, there are 10 of them. However, only 3 of the WN8H stars show a well-defined nebula around themselves. These 3 stars are our sample. The nebular material consists of gas and dust, both of which interact with the UV flux of the central star, and so cannot be treated separately. For this reason, in order to get information about the properties of these components of the World-Rayet Nebula, we use the photoionization code CLOUDY. CLOUDY works with a scheme consisting of the central star surrounded by the gas and dust distribution. CLOUDY needs as input parameters the shape of the spectrum of the central star and its luminosity. Also, CLOUDY needs the density profile of the nebular material and the dust grains parameters. In our models, we use spherical silicate grains. Our models were constrained by dust and high-noise gas emission and measured from observations, and we use the shape and flux of the infrared photometry to fit our model. However, in order to calibrate the quantity of ionized gas, we use the H alpha and H beta emission lines and radio continuum observations. This can be done because the transmitted continuum given by CLOUDY can be used to calculate synthetic photometry and emission and fluxes, and measure fluxes of the emission lines by synthetic slits. The dust emission from World-Rayet Nebula can be studied within 12 to 500 micron range of the Spitzer, Weiss, and Herschel observations. Then, our first targets were M167 and RCW58 around World-Rayet 124 and World-Rayet 40. Here I showed you the multi-wavelength infrared images of these 2 nebulae. In case of M167, you can see the bipolar shape and the clumpy structure. In case of RCW58, you can see that the spare observations show extended infrared emission. This hampers a global study of the nebula. Then we select 2 representative clones of the global properties, LC and RC clones. Then here also I showed you the schemes of the models of the H nebula. We can reproduce the observations in optical and infrared range of wavelengths. In case of M167, we need a model consisting of 4 zones, 2 zones in an inner shell and 2 more in an outer shell. On the other hand, we model LC and RC regions as a multi-layer clones. In the tables, I showed you the gas and dust distribution of the H model. For M167, you can know that only zone 3 has dust, same as the other layers of the LC and RC models. In these other layers, we have 2 populations of grains. One population of small grains and another one of large grains. Here also in the figures, you can see that the set obtained from infrared observations and the nebula of the nebula and the synthetic photometry from our models. We have a good fit with the observations. Okay, then from our models, we can conclude that we need an inner layer with only gas and a dusty outer layer in order to fit the optical and infrared observations. Furthermore, in order to fit the infrared set, the dusty shell needs dust grains as large as 0.9 microns. This maximum grain size support of 0.9 microns support an eruptive scenario for N167 and RCW58 for its formation. In the single star context, the dust formation stage could be during a LBB phase. However, it is possible to estimate the initial mass of the well-rayed progenitor star with the nebular mass calculated from our models and taking account the current mass and the mass losses during main sequence phase of the well-rayed star. For both well-rayed 124 and well-rayed 40, the initial mass is around 40 solar masses. This ruled out the possibility that well-rayed star had a LBB phase. Other eruptive scenario for dust formation can be common envelope scenario.
2 minutes.
Thank you. There are clues that allow us to think that well-rayed 124 and well-rayed 40 stars have a compact object as a companion embedded within a dense stellar wind. One of them is the bipolar morphology of N167 and the torus fold-on shape in RCW58. Another one, it is the dynamics of H nebula. Since N167 consists of a hollow shell of ballistic clumps moving at 46 kilometers per second, while RCW58 is a clumping ring-like structure expanding in a range of velocities between 30 to 87 kilometers per second. In a closed binary system, common envelope can lead to ejection of the common envelope and a Tiger binary. Also, the common envelope expansion after the end of the dynamic inspiral evolves into an ordered shell-like structure and lake times. We estimate the kinematic energy associated with expanding clumps in N167 and the ring-like structure of RCW58 using the nebular mass calculated from our cloudy models and the measured expansion velocity. We estimate the kinematic energy on the order of 10 to 47 ergs per second for both of them. These energies are similar to that estimate for outbursts in recent optical transit events that have been associated with mass transfer process in binary systems. Also, lastly, the ejectile common envelope systems have been shown to be an ideal environment for dust formation. In conclusion, our analysis allows to propose N167 and RCW58, as well as the progenitor stars, as first observational evidence of the post-common envelope evolution in the nebula around massive stars. And that's it. Thanks for your attention.
Thank you, Palmira. That was a great talk. And I'm sure there would be questions for you. I think there's several people here that I know in the audience that have worked on dust in common envelopes and hydro simulations. So I invite them and everyone else to raise their hands. Fabian.
Yes, many thanks for that brilliant talk. I had some internet connection problems in the meantime, and so I might have missed whether you know anything about a binary companion to these stars, sort of a close binary companion or anything else. And yeah, how that is sort of constraining the common envelope scenario, or if there is no companion, for example, but this might be actually a result of a merger.
I think that I don't understand well the question. It's about the binary system in world, right? We try to constrain our models to this scenario of common envelope using as the main clue the maximum grand size, because we need a ejection scenario with a large mass loss rate, then together with this size of grains and the dynamics of the nebula and the morphology, this can help us to,
Yeah, so my question was more pointing towards whether the star that you see in the center, is it single or is it a binary? And I probably missed this because I had internet connection problems.
Okay, thank you. It's not possible see clearly a companion of the World-Rayed 124 and World-Rayed 40 because the World-Rayed stars are characterized by dense stellar wind. But this clues of the morphology and dynamics help us to understand that there is the possibility that these stars have a companion.
Enrique, do you want to ask your question?
Sure. Thank you for the nice talk. So I was just slightly confused by the last slide. So you have the kinetic energies, but you list them more like luminosity. So which one is it? Is it 10 to the 47 ergs, the total energy deposited into the nebula, or is this ongoing, 10 to the 47 ergs per second?
Okay, this energy kinetic energy, I'm sorry, is based on the velocity expansion and the, I'm sorry.
Okay, all right, thank you.
Okay.
For the last minutes of this session of today, sorry, hi Guy, I'm going to ask you to post your question on Slack. I would like to take 10 minutes or so we're running then 5 minutes over time, to maybe have a general discussion. So any general topics that anyone would like to discuss, I want to open the floor for it. I've already seen some things coming by on Slack. For example, the question from Emily or the question from Sagiv about dependencies of alpha on the structure of the star, whether or not it's convective or not. This sounds like a great topic to start off a discussion. Does maybe anyone want to comment on this, or maybe Emily or Sagiv want to pose your question the way that you intended?
Sure, I can. I can talk
that's
about.
Okay, go ahead.
Yeah. So my question was just basically, what kind of things do we know about the systems before we start trying to figure out their final systems that would be used to constrain alpha? And that was a question for Avishai. I don't know if he's on the Slack or not. Or a question for anyone. I ask because my work is showing that the efficiency can be is affected by the internal structure of the primary and other things like the mass ratio. So I'm just wondering if anybody else has looked at kind of what affects alpha, what alpha can be a function of.
I raised the topic yesterday also about the amount of shrinkage and how that depends on the companion star, where I saw some differences in a published paper in the literature. Things getting very quiet on the side of...
Yeah, one parameter, of course, if you notice a talk by Avishai Gilkis, he had to go to a wedding. I don't know if his wedding or somebody else. But anyhow, this is his usage and some other models of alpha equals 7 to 10. So how do you get alpha of 10? Of course, you need another extra energy source. It cannot be a combination. So one parameter is whether accretion can give you the energy by jets, because radiation doesn't work. So it must be jets. And I think, yes, jets can give you alpha equal 2 to 10. I don't think much more than 10 because of the negative feedback effect. So then it depends heavily on the companion. Neutron star and black hole can be very efficient in giving you the energy. And I think, yes, when you form binary neutron star, black hole, black hole, black hole, in the second common envelope, in the first one, maybe you don't have it. Second one, you have jet, which can increase alpha a lot. And yes, another problem is where does the energy of the orbital energy goes to, and some of it will be radiated away. But another sink of the energy is we always assume alpha that we just eject the envelope at velocity 0. But if we use all the energy, the orbital energy to eject material, no radiation, still we can eject a little bit mass at very high velocity. Even if we eject the mass at the escape velocity, we use about twice its binding energy. So even alpha equal 1 will require ejecting only half the envelope at the escape velocity, which is the typical mass loss. So the parameter also is what is the velocity of the ejected mass, and this depends on mass ratio, eccentricity. For example, maybe eccentric orbit can send less mass, but more at higher velocity. So this will reduce alpha. This is my small addition to the discussion.
So no, you mentioned, for example, when you're talking about jets and how this can increase alpha, for example, you say this in context of compact object companions, but what about, I mean, the majority of common envelopes, which would usually not have a neutron star or black hole
Majority
companion.
depends.
What do you think?
When you form neutron star, black holes through the common envelope evolution, in many cases you have, when the first star evolves to a giant, it doesn't swallow the companion because the companion is a massive main sequence that manages to bring the first star to synchronization. You get into the second, you get into a common envelope only when the second star expands to a large star. So in forming neutron star, black hole in the common envelope scenario, not triple that perturb the orbit. It can be a triple common envelope. This is something else. Then I think you do have many. In other cases, we have white dwarf or main sequence. I think main sequence can launch a relatively strong jet, much weaker than neutron star, but also they enter the envelope of much lower mass stars. Mm-hmm. White dwarf, I think, have a problem to launch jets at a high rate because the moment you accrete above 10 to the -5, 10 to the -6 solar masses per year, depending on the white dwarf mass, you start nuclear burning. So the white dwarf companion itself becomes a core of the giant. You have two cores now. So I think main sequence star can also launch jets. And we had the talk the first day and by Ake, and we will have the last talk by Hans van Winkel, that they see main sequence star accreting mass and launching jet. Okay, they accrete it from circumbinary disk, but I don't care where do they accrete the matter from.
Well, we see observations of this in some double core planetary nebulae, right, with the main sequence and white dwarf, and there's clear high velocity bipolar outflows there. So,
yeah, I assume all of these are jets, yes, that were launched by accretion disk around the main sequence companion, especially if you see precession that collimation by a large envelope cannot explain.
I think accretion was one of the things that I was interested in, especially about these carbon dwarf stars. So there's amount of accretion of 1/100th or 1/10th of a solar mass. To me, during a common envelope, seemed a very large amount. I don't know what other people think of this, or if this is something that could happen in fallback, or in the phases leading up to the common envelope, or any other observations where we maybe also see signs of accretion related to common envelopes events. What are other people's thoughts on this?
Someone mentioned the carbon stars today, that they seem to be accreted mass.
Exactly, yeah. So that's like 100th or a couple tenths of a solar mass during a common envelope phase. To me, that's a lot, but
yeah.
Did you try just using the Eddington rate and just seeing how, over the duration of the common envelope, assuming some time scale, maybe 10 years, with that, I haven't plugged in the numbers, but you could, that could be easily checked.
Eddington limit has no role in neutron star and black hole. This is my view.
Neutron star, yeah. If this is neutron star and black hole that you're talking about, no.
These are white dwarfs with main sequence stars, right? But
yeah, so white dwarf and main sequence, I think Eddington is probably the best.
I think you should argue yourself. You have a work that you showed the jets can take the energy, so you can even.
So Amy will be presenting tomorrow, where we have a new paper with coming out with jets in our common envelope simulations. But there's nothing. So if you allow accretion to happen without including radiative feedback, it can be very, very high. And that could be the case for neutron stars and black holes, where you have neutrino cooling, as was mentioned in some of yesterday's talks. But for white dwarfs in main sequence, it's much more difficult. So it's still possible that you could have super Eddington accretion rates, especially if you have jets, right? And so you don't have the spherical geometry. And then some people believe in these advection-dominated accretion flows that could be highly super Eddington, but I think it's still controversial. So we've been assuming in our latest work that the accretion rate onto the companion, which is a point particle in the model, but basically main sequence or white dwarf, will be of order the Eddington rate. And that's sort of we're treating that as sort of an upper limit for now. And we find, Amy will discuss it in more detail, but we're basically finding that at least during the short duration of our simulation, the jet kind of gets choked, gets quenched, and does not really change things much compared to the no jet simulation. But if one if one were to run the simulation for much longer, then you could ask what would happen, and that we can't simulate directly because we just can't do it. But analytically, one can estimate how much energy you're injecting into the envelope and over the time scale, like 10 years or so, and it would be probably negligible. Of course, there will be an efficiency there as well, so one can't know exactly how much that can contribute to unbinding, but the estimate says that for a white dwarf or main sequence star, it probably won't make much of a difference, but for a neutron star or a black hole, it definitely, there's definitely a possibility that it could. And that's just from a very simple order of magnitude estimate. But anyway, Amy will show the simulations tomorrow.
Ursula?
We should know that we simulated mergers of neutron stars with white dwarfs. This is not the same, of course, scenario, but there's a lot of material extremely close to the neutron star. And which is actually much closer than what you typically have in a common envelope in some sense, because the white dwarf material is much more dense. Even in that case, direct accretion to neutron star was extremely low in our simulation at least. So it's not very clear how strong jets can you produce. We could have high feedback, okay, because much of this material is not accreted because of feedback, but less and less material gets to smaller and smaller separations. So you still have potentially limited amount of energy that you can introduce from this accretion. As I said, these are very different simulations, not directly related, but I think they put in some sense upper limit on the amount of energy, because accretion from much lower density gas, I think, would produce far less energy, and much more feedback would eject this material much before, and might not even contribute too much, even in the case of neutron stars. Anyway, that's just possible caveat to all of this.
Ursula, go ahead.
So I have a question to the pop synthesis, you, Sylvia, and Ashley, as well as people who do 3D hydro, as well as the people who understand MESA and mass loss in MESA. So we got this double white dwarfs and this idea that you have potentially a second common envelope. I realize that's controversial, but let's say that you have a post-RGB, post-common envelope systems with a horizontal branch star, happy. And then let's say that the star, which has been quite stripped, will be able to go up the AGB. So it's now re-expanding and going into a common envelope again. So I question, what does that common envelope look like? And, the immediate feeling is that it just leads to a merger because the two stars are so close to each other, they'll go into a common envelope right away as soon as the post-RGB stars starting to re-expand. And but that I don't think is what the population synthesis does, right? I don't think you still manage to get a surviving binary that gives you a double white dwarf. So how does that work? And perhaps this could be simulated. Not that the simulations tell us something right necessarily, but hey.
So it really depends on the.
Go ahead, Sylvia.
It really depends on the mass of the stripped star as to how large that giant becomes. So for low mass and very high mass stars, it actually doesn't swell up much. And then it's hard to survive such a mass transfer phase. But there's this sweet spot between, say, 1 and 2, 1 and 4 solar masses, where you do expect from stellar calculations that you get these large giants, which are in that sense pretty similar to an RGB star. So, our best expectation and extrapolation is to model that in the same way as we would do a common envelope phase on the RGB.
But the companion is right there. So how can they expand?
Well, because so the question is, how is that binary formed, right? So if that binary is formed, you want the first
regular.
Definitely
it's a regular common envelope on the RGB, but now you got your binary where the primary is going to want to go to the AGB, but it's not going to be able to go to the AGB because it's got a companion right there.
I think in most of the cases that we find this in POP-SYN, that first phase of mass transfer would be stable so that your orbit widens, and then there's room for that helium giant to fill the rush slope.
Also,
or you have an alpha with a very high value of alpha, something. So indeed, you're right. That first orbit or that first phase of mass transfer cannot shrink the orbit a lot. Otherwise, your giant is going to be small when it fills the rush.
Okay, so basically, yes, it's not two common envelopes. It's something else plus a common envelope.
Likely, yeah. Alexei has his hand up.
Well, I just want to comment because we've done some mesopopulation synthesis studies with Joris Voss of short periods of dwarf B stars with main sequence companions. And the thing is that we do sometimes have, quite commonly, we have helium burning stars or helium stars, or they're called SDB stars, on short periods of like between hour and few days orbits. And they have main sequence companions, but we also observe them to have sometimes white dwarf companions and brown dwarf companions. And SDB stars are made entirely out of helium, and helium is burning. So eventually, after helium is burnt, it will enter the shell helium burning phase and will expand to the giant. And in some cases, it will enter a second phase of common envelope if the companion is low mass enough. For example, we have observed systems of brown dwarfs plus SDBs on an orbital period of like a few hours and even shorter. So that will just happen. I mean, and just one other comment is that at least from meso simulations, it's very hard to make a horizontal branch star on short period post common envelope. So usually either we strip everything and we get SDB star, or if we so in other words, it's very hard to ignite. It's very hard to retain a large amount of hydrogen and to do common envelope phase, at least based on meso, for solar-like masses, kind of.
I feel like at this point, I probably should give everyone the right to take their break, because otherwise, Haigai is not going to be happy with me when he's chairing the next session and everyone's going to be tired. So if you want to take a break, go for it. I also noticed Haigai still had a question in the chat, so I'm happy to chat a little bit about that, whoever wants to stay, but feel free to go get lunch or go get dinner or take your break.